Okay, so at the end of last lecture, I started talking about heuristic for the C0-based strong Onsager conjecture. And I've introduced the relaxed system, which consists of the Euler-Reynolds system and the relaxed local energy inequality. And then I start solving the low frequency part equations so that to decide the coefficient functions, meaning that so our answers looks like this. Again, the perturbation consists of the low frequency part and high frequency part. And I divide into two parts. The first part looks like this, AR, WR, where AR is, okay, let me first write it, A phi. Okay, here AR. So the first part will be used to correct the error RQ, the Reynolds stress error RQ. And the second part will be used to correct the error phi q, the current error. Okay. So, and again, this is low frequency part and high frequency part will where I use the Mikharov law, and low frequency part and high frequency. And the WR, as I mentioned, is Mikharov law. So let me just write it in this way. So there's actually summation, and xi, this is associate function, it's xi r, and then for the current error corrector, let's say xi prime and associate function. Okay. And what I said is the following. If you choose this associate function in a special way, well, first of all, the mean xi phi r is equal to 0 on a torus. And this is just for the spatial localization. And then you also have square mean is equal to 1. From here, we actually get the size of AR as square root of RQ, 1/2. And then the last condition was the cubic mean is equal to 0. And this way, you can drop the contribution of the Reynolds corrector from the low frequency part equation for the relaxed local energy. Okay. And here, it's also same, the mean 0 condition. Again, for the frequency localization. And then when we solve the low frequency part equation for the, again, relaxed local energy inequality, we put this cubic condition because the nonlinearity there was the cubic. So cubic mean is equal to 1. Then from this condition, we also have the following relationship. And lastly, actually the current corrector contributes to the low frequency part equation for the from the Euler-Reynolds system, and there we put the following relationship. I think A phi square, and then the mean square mean has the same size with the arc. And this give and okay, and since this one is homogeneous, meaning that when you measure this Mikharov law with different LP norm, their size are all essentially same, right? So when you measure L2 norm, this also has a unit size, and from here we also have the relationship phi q is actually determined by RQ raised to the power 3/2. Simply just plug this into here. Okay, so now with this relationship, let me show the heuristic computation. But I won't go into all the errors. As I gave you a spoiler, there is a error which generates the condition the beta is less than 1/4. So I will just mention one of the error which give this condition. So first, let me recall the relaxed local energy inequality. So this is the relaxed inequality that I gave you, but actually what we solve is the following. So instead of this inequality, what we solve is minus some measure which is determined by the initial approximate solution. So this is not initial data, this is initial approximation. So at the zero step, initial step, you generate the this negative measure, and after that, you don't generate any negative measure. And now, so eventually, if you send Q to infinity, this will remain, so you will get inequality, the local energy. And here, again, the point is, since this is generated at the initial step, if you write the equation for W, which is the perturbation, then there's no contribution of this, because both equations. Okay? Okay. And now, let me introduce the current error called Nash current error, which looks like this. So it's again defined as a solution to the following equation, plus 1, let's say n. The right-hand side was this, I think. Okay, I think it was. Yes. Okay, so if you ignore RQ, this one almost like Nash error, but you actually have extra W. So that's why it's called Nash current. And now let's do the estimate by using our this size relationship. Then again, from the inverse divergence, well, first note that since we cancel out the low frequency part, this will only have the high frequency, lambda q plus 1, W tensor W. And when you invert the divergence, you have again 1 over lambda q plus 1. And then you have a gradient of lambda, gradient of UQ, and then W tensor W. This one has just unit size, right? I think I missed something. This is not unit size. So this can be written as A square lambda q plus 1 and building block flow. So from here, I have size of RQ. Okay. There are two cases. So when this one is the current corrector and the other one is when it's the Reynolds corrector. But actually, if you use this relationship, they are both at the same size. And the size will be just RQ. So the size will be either RQ or IQ raised to the power 2 thirds. These are things. This A square. So like the W, okay, I think I should write more carefully. The W, I just use abbreviation as A times W. Okay, so this is just coefficient. So it can be AR or it can be A phi. Okay, and let me continue. As mentioned earlier, I'm still following the same inductive bound that I introduced for the Onsager conjecture. And for the inductive bound for this phi q, you use this relationship. Okay, then the size is given as follows: q plus 1, lambda q, delta q 1/2, and this is delta q plus 1. And we want to put this one into phi q plus 1, whose size is RQ plus 1 raised to the power 3/2. So let's say we want to put 1 over 10 delta Q plus 2 3. And now if you do the computation, you can actually see that, okay, I think I did the computation. In the exponent, this is what you're gonna see. So here, from here, you get the condition beta is less than 1 plus 3b. So when b is close to 1, you get 1/4. Okay, and now you may ask, so what's happening here? So why does the beta get worse? The reason is the following. So question, why beta get worse? So first, let's think about the local energy inequality. It is actually obtained by taking, I'm just going back to this, let's say smooth, just imagine smooth solution to the Euler equation. The local energy inequality is obtained by taking the inner product of the momentum equation with velocity, right? And if you compare this with the Euler-Reynolds system, in terms of size, this one has extra UQ, right, compared to the Euler-Reynolds system. So in the error, you expect this type of form, some error which looks like a Reynolds stress error, and there's extra W, right? So expected size of the error is following, like RQ plus 1 and WQ plus, or WC0. So this is expected, which is delta Q plus 2 times delta Q plus 1, 1/2. However, the size that we want on the right-hand side, the required size, is delta Q plus 2, 3 over 2. So this is much smaller. And this discrepancy makes the beta worse. Okay, so now let me move on to the L3-based Strong-on-Sagar conjecture and explain how this restriction can be improved by using intermittency. Yes, the 1/7 is what we can achieve so far. So there's still a gap between 1/4 and 1/7, which requires, so this is heuristic, and to make the heuristic really work is another story. Yeah, it often requires a lot of the development of technical tools. Any other questions? Okay, then let me continue. Okay, so in the S3-based Strong-on-Sagar conjecture, we want to construct a solution which is intermittent, meaning that when you measure the solution with different LP-based norm, you want to get different differentiability parameters. Then at the building block level, you should see this feature. So if you just think about the original Mikhailov law, as we just discussed, when you take LP norm, their sizes are essentially same, right? But for this, if you want to solve L3-based Strong-on-Sagar conjecture, you should use some other building block flow which has an intermittence. So let me first introduce intermittent Mikhailov. Roughly speaking, you can consider this as a spatially localized version of original Mikado flow. And what I mean by this is the following. So for simplicity, let's just consider in one-dimensional setting. So in original Mikado flow, the associate function looks like this. It's just a compactly supported smooth function, and it's mean zero. So perhaps you can imagine, and let me draw a better way. You can imagine some function like this, right? In one dimension. And now what I mean by spatially localized one is that now you just spatially localize, concentrate this, then you get the, I think concentrate it first. So you just make a concentration of this, and then it will look like this. And to measure the amount of the spatial concentration, one can introduce the parameter R, which is called the intermittency parameter. And if you want to keep this, for example, what we want is the L2 normalized flow, then that will determine the size of the amplitude. So in the case of L2 normalization, the size should be R minus 1. So now let me give some comment about this parameter R. This parameter lies between between 0 and 1. And as I just mentioned, it measures the amount of spatial concentration. In particular, if you send R to 1, then it goes back to the original Mikado. So here, you just imagine the scale is 1. Right? So when R goes to 1, it goes back to original 1, which is like, so I just use, okay, maybe it's better to use a less intermittent. And then if you send R to 0, you have more concentration, so it's more intermittent. So if you want to use intermittency, what you want is you want to choose this parameter very small. And now let me introduce the building block flow. Now, so there will be a direction K, and then rescaling parameter lambda Q plus 1, and let's say RQ. And originally, it looks like this, so just direction of K, and then psi K, and lambda Q plus 1, K per X. So this was the original form, like original Mikado flow. And then now we introduce this intermittency parameter RQ. So the associate function is replaced from here by, from this by this. And then we also include the factor RQ here. The reason is that we want the derivative cost of this function still remain as lambda Q plus 1, but the derivative cost of original function is already R inverse. So you periodize by this number so that the derivative cost still remains as lambda Q. Normal. Okay, I didn't specify that. So if you want, later, if I use this for the Reynolds corrector, I will put the index R. So this will mean that they normalize in L2, right? But if I use phi, so if I use this flow for the current corrector, then it will be cubic, L3 normalized. So, but I didn't go there yet. Okay, so let me describe this in the physical space. So in physical space, so again, this will be supported. So, okay, maybe in the original, so before rescaling, this will be supported in a pipe whose thickness is R. So the radius of the, this pipe is just R. And then, you can draw a thin pipe with that. And then now you rescale by lambda Q plus 1 RQ. Then you will see the size, the pipe, whose thickness is lambda Q plus 1 inverse, because originally it was RQ, RQ, and then you rescaled by this factor, then the size of the pipe will be lambda Q plus 1 inverse. And since you periodize by this number, the spacing between the two pipes will be lambda Q plus 1 RQ inverse, because it's periodized. Okay. So if you send RQ0, well, the thickness of size of the pipe remains the same, but the spacing between pipe gets large. So it's a really intermittent. So, okay, it depends on like whether you use L2 normalization or L3 normalization. Yeah, if it's L2, then you have this height. Okay, this is one-dimensional picture, so the height will be actually lambda 1. The height of the associative function on this pipe, the amplitude. But maybe I will give an answer to that question. So if you measure this building block flow in LP norm, then the LP norm is purely determined by this intermittency parameter, which is RQ. And there are two cases. If it's L2 normalized, then what you have is 2 over P minus 1. So this is the power. But if it's L3 normalized, you will see the power 2P and 2 over 3. Does this answer to your question? Volume?
No, I was thinking like you are concentrating.
Right.
So right now, how much volume is it
there? Volume of what? The pipe or?
The pipe, yes.
To volume of the pipe.
I'm thinking like you
are it just
domain and you are just
right?
dividing it, right? And each of these you have this pipe.
Right.
It's not occupying the entire one.
Because
it's concentrated.
Right.
The volume is carrying.
So it's just like this one square and the length is 1. So
it's like two-dimensional.
Right. Right. So in each periodic box, that's the dimension of the body.
Is it something different from Navier-Stokes?
You mean the solution?
The construction.
There you can also use intermittent Mikado flow, but the choice of parameters are also very different there. There B is greater than 1. B, much larger than 1. But yeah, they still use this type of building block flow. But the purpose is slightly different. So there, the difficulty is how to handle this extra diffusion term. And then diffusion term, you have a gradient, right, which costs a lot. But to compensate it, you can measure in L1 norm. And there is a gain from intermittency when you measure in L1. So that's why they want to use intermittency. But yeah. Okay, and in here, the purpose is to, the motivation of Strong-on-Sagar, LC based of Strong-on-Sagar conjecture itself was the incorporating the intermittency, and also more at the technical level, we want to use the structural difference between nonlinear term, but I will give a comment on that after a few minutes. Yeah, I will. So yes, that's one of the questions. Yes, I will do that. Okay, but before we continue, let me also talk about how does this look like in the frequency side? So the original Mikado flow has the frequency localization at lambda q plus 1. But now, since the periodicity is just lambda q plus 1 RQ, so you actually have wide range of frequency. Lambda q plus 1 is again still derivative cost, so its a maximum frequency remains the same, but the minimum frequency is lambda q plus 1 RQ. So actually in the frequency side, we no longer have a localization. But of course, we'll choose RQ to so that this number is greater than lambda q for the purpose of learning Nash's iteration. Okay.
This one has an extra term, like an extra gradient, which you also have to control at the same time. It's a cubic kind of term. So here in this particular right-hand side equation, just like earlier, you tried to cancel some parts of RQ by controlling the
Square.
W. Couldn't you try to now cancel the freedom not there for us anymore after choosing the others?
Well, I don't see that freedom, but so maybe one way to think is the way to derive this equation was following. So you decompose U into the some like averaging part and the high frequency part. And this one was actually produced by divergence of the -1/2 and low frequency part of this. So it's quite natural to match this with this if you think about how this equation is derived. But I don't know if you choose some magical building block flow as last law as yesterday. But I don't see that freedom. It's unclear. So now there are several questions. So first question is, so how does this intermittency help improving the differentiability parameter? So as you just saw in the C0 scheme, we had the restriction beta is less than 1/4, but in the L3 based scheme, as you saw from our theorem, we can actually go up to 1/3. But of course, in L3 scheme means that when you measure the solution with L3 based norm, then the associated the differentiability parameter goes up to 1. Okay. So this is the first question. And as Ujjwal just asked me, what should be the right amount of the intermittency? So how do we choose RQ? So first, as a partial answer to the first question, let me talk about this. The benefit of intermittent Mikado. Okay, so if you recall how we had this restriction, actually the restriction comes from this relationship. So let's go back to here. And this relationship actually comes from this. But now the observation is the following. If you work in the C0 scheme, we set the size of the square mean is same with size of cubic mean, right? Because there's no intermittency. But now we have intermittency, so this is no longer 1. So this is L3 normalized. If you use this LP norm estimate, okay, so here, what do I need? Yeah, if we just use that, the relationship that we get is the following. the phi, I think phi q, 3, 2 over 3. And then here we gain a factor, okay, phi q. I think this is r. Okay, I think eventually this should be r q inverse. So you get a new relationship, which looks like this. So now compare with the previous case. Now our current error allow much larger error. And this can perhaps solve the discrepancy that we just observed. Okay. So that's the partial answer for question 1, but I will show you how we get this beta is less than 1/3 later by again showing the heuristic estimate for the Nash current. Okay? But before that, we need to determine what should be the intermittency parameter, and we also talk about what should be the inductive bound. So I think next I'm gonna talk about inductive bounds. Any questions? Okay. Sorry, this? Yeah. Sorry, what's the question? Yes. Yes, this one? 2 over 3. Sorry. Yes, you're right. 3 over 2. Yes, that's correct. Thank you. Okay. And then before I introduce the inductive bound, let me just make also another comment. If you work, so when you work in the C0 norm, the nice part is when you measure multiplication of two functions by C0 norm, this is controlled by C0 norm of F and C0 norm of G. The problem is you can't do this in LP norm. If you have LP norm, in general, you need to use holder. It's not like LP norm is bounded by the LP norm of each function. So this is not true in general, but if F and G has a frequency separation, this is possible. Because let's say G has a much higher frequency than F, then from the perspective of G, F is almost like constant function. So you can actually take it out. So for when F is constant, this holds. So that's sort of idea. So let me introduce, just to be more precise. Let me go this way. Decoupling. Which says the following: if P, let's say if P is between L1 and infinity. In the case of infinity, it's trivial, so we don't consider. And let's say F and G are periodic function. So let's just define on a torus to R. And it satisfies the following: the derivative cost LP is lambda, and there's a size of F. And then let's say G is periodic with the period kappa. So let me write kappa is the period, kappa inverse, period of G, and its inverse, and say this is much larger than the derivative cost of F. Roughly speaking, this is higher. G has a higher frequency. Okay. And then also G LP norm is bounded by CG. Then you can show FG LP norm is bounded by CF times CG. Yeah, you can consider it like that. The idea of the proof is the following. So first, we want to compute this bound. and then you start from torus. But first, you divide the torus into the small cube, whose side ranks is a kappa inverse. Right? And we call each cube by Tj. So here the point is that this has side length kappa inverse. And on each cube, you can actually write the expansion of Fp as follows. So what I want to, so on Tj, so this is very small size of cube compared to the, you know, the oscillating length of the F, right? So on this cube, this is almost like its average. One can write it this way, F Tj plus F minus its mean. Okay. I mean, okay, I'll just, I'm not sure it matters. Okay. And then you can show that this is actually small because, well, if you just use the, I mean, you write it this as the Tj Fx minus Fy dy, and then if you use just the mean value theorem, then this can be bounded by the 1 over kappa d F primum in Tj. And then if this size is not too small, you can just keep iterating this process. So you just plug the F into here, and then has again the expansion. And so now if you take 1 over P, then this is just bounded by the mean of F plus the higher order term. And here, if you use just holder, you can also write it this way. Yes. Okay, so this is a leading order term. And now if you plug this back to here, you can easily see that this is constant on the Tj, so you can just take it out. And if you do some computation, you can see that why this is bounded by Cf and Cj.
Quantify what would be exactly the threshold of the difference.
So as long as you have a gap, it's okay. So you have this is a periodic function, and this is has a derivative cost. And if as long as derivative cost is smaller than kappa, okay, it doesn't need to be really like has a big difference. As long as you have a bit of room, then you can just keep iterating and make it work. Yeah. No, I think they did for some specific piece, but I mean, idea works for any P. At least, okay, if you want the reference for any P, we wrote a lemma for this, so that's one reference. But the idea is same. Okay, you also have. Okay. Really? Okay, so they didn't do this way. Okay. But did you do this way, or you also did in the different? Okay, so this is simple. Okay. Yeah. So we follow Laszlo's idea.
So, I mean, this is in general false.
Yes.
Because the high frequency interaction only is getting good feedback.
Yeah, I mean, this only works if you have this specific setting, but otherwise. Okay. Now let me introduce the inductive bound. Okay, so we use the same parameter, lambda q, which was the double exponential function in q, and then delta q also remains the same, lambda q raised to the power 2 beta. And then, okay, I will first write down and explain why it's designed in this way. So you measure the stress error by L3 over 2 norm, and the size is again, we use delta q plus 1, and then you consider L1 norm of this current error, which is delta q plus 1 and 3 over 2 RQ inverse. And then if you compute the size of UQ, let's say when n is greater than 1, then you can do that in delta q 1/2 RQ 1, and there's a derivative cost. This is the one. And then if you, I'm not sure you remember our statement of theorem, we eventually want to construct our solution in the following space, B E 1/3 minus 3 infinity, and there's also intersection with L infinity minus. So we're gonna also propagate the size of L infinity. And since we want almost boundedness, when you measure in L infinity norm, let's say this is bounded by 1, and then phi q, L infinity norm will be RQ inverse, and then the size of UQ, and let's use M infinity will be bounded by lambda Q M RQ, what was it? RQ. This one actually works for any M.
Sorry, so bounded by 1 means it changes another. But that's why you are not in the infinity.
Yes.
What motivates this choice of 3 by 2 or 1?
I'm coming, yeah. So that's, I will explain now. So here, if I just briefly talk about the motivation. So the first thing that we want to know is when you measure our velocity with S3 norm, you want to see how far the differentiability parameter goes. So recall that our W looks like this. Just I write it in terms of size. So 1/2, and there is a building block flow, and then there was a phi q 1/3, and there are building blocks. And then you apply S3 norm here, because that's what we want to know. And then you apply the coupling lemma, and you can see that the information that we need to know is actually, so if you take S3 norm here, you need S3 of 2 and 1/2. And then this one, we need L1 norm information. So we propagate, we inductively propagate the estimate, L3 estimate of RQ and L1 norm estimate of phi. And then you may also wonder the size relationship is again the same. Once you put the size of this 3 over 2 norm as delta Q plus 1, again using this relationship, which is not here. This one. So again, using this relationship, you can decide the size of phi q and UQ. Okay, so I think now, okay, before we go to the Nash current error, now we need to decide the intermittency. So let me answer to the second question. So if you just think about the benefit of the small intermittency parameter, you just want to choose R very, very small, right? But there's also difficulty because eventually what we want is almost bounded solution. But if intermittence is too small, it has too strong spatial concentration, so it can destroy this L infinity bound. So let's consider the Nash oscillation error. No, not Nash, the oscillation stress error. In L infinity norm space, which will actually give a lower bound of this arc. Okay, so which, again, let me recall. So this error was given as the following form: inverse divergence of this okay, let me just be precise. And this one was written as, I mean, you can write it as follows: A square and then W tensor. And previously, by using the mean part of this, we cancel out this. So what's remaining is the part whose mean is not equal to 0. So maybe you can write this one as actually divergence of inverse A square. But here, what you need to be a bit careful is that since this one now starts to have a low frequency, right? So that's the part that we need to be careful. But actually, in terms of L infinity norm estimate, the worst case is at the highest frequency. So let me just, at this moment, I will just say, I will just only consider the following piece. Let's say, I don't know, I'm not sure, the last shell. So this one is lambda q plus 1. And then I will discuss later about how to handle the low frequency. But anyway, for this, if you again do the L infinity norm estimate, then you will get 1 over lambda q plus 1. And then this is RQ, which is bounded by 1. Okay, I mean, you can also think about the current corrector part, but they are in the same size, so I won't go into that. And then here, what do I get? The something here, there's this. Okay, something is missing here, divergence. Then okay, and then from this differential operator, we get lambda q, and this has a size 1. And here you get the size RQ minus, and we want to make this one bounded. Then you will get the lower bound, RQ is greater than lambda q plus 1, 1/2. So this will be actually our choice of the intermittent. So like we want to choose, so if you want to get full benefit from the intermittency, you want to choose very small RQ. But to make this our eventual solution to be almost bounded, it needs to satisfy this. So this is the lower bound. But you want to choose smallest one, so you just choose the smallest one. Okay, now let's go back to the Nash current error, and which will give an answer to this question. Well, I mean, you can also have maybe higher intermittency, but you wouldn't get the regularity almost close to 1. Just from the perspective of using intermittency, smaller one is better. Right? If RQ getting close to 1, then it's just going back to the homogeneous scheme. I mean, C0 scheme. All right, so Nash current. So the error looks like this, the phi q plus 1 n. And then it's defined as follows: divergence inverse q w. And again here, let's also consider the guy whose frequency is around lambda q plus 1. Because when we do this estimate, we got the beta is less than 1. Sure.
It seems like you mentioned that W has frequency, now it's in a band, right?
Right. So here,
take advantage of divergence inverse to the fullest because
so yes, so actually here you have wide range of frequency again, but the worst case is actually when the size is lambda q plus 1. Okay, this will be unclear at this moment, but later I will write some lemma, because when you have some projection to the low frequency, you also have a gain in L infinity norm size. So that I didn't go yet, but I will introduce the lemma in a minute. But at this moment, all I can say is this is actually the worst case. So I only consider when the projection is applied to the lambda.
But also 3/2 norm we have to calculate. RQ 3/2. And that will also verify.
So here, so the reason I introduced this computation is that there is just a lower bound of RQ. And of course, in practice, you need to check everything. And now I'm gonna use this I'm gonna use L1 norm of the current error. Because so previously we talked about Nash current error, and from there we got the beta is less than 1/4 in the C0 scheme. And now
picking the most difficult.
Yes, I'm just picking the worst case. Yeah. For any other case, you can just look at the page, or you can just do it by yourself. Yeah. Then maybe doing by yourself is easier. Okay. So now again, let's consider the last one. And then if you take, so now we want to compute the L1 norm. And then from inverse divergence, you get lambda q plus 1. And from here, okay, so let me first expand this. So this one looks like a square, and then there will be lambda q plus 1 and w. So if you apply the decoupling lemma, here you will have q a square, which are low frequency, and you apply L1 norm. And then for the remainder, the high frequency part, we apply L1. And then here I'm gonna just use holder, then it's 1q plus 1 and L3 norm of uq. And then there are two cases when this one is a Reynolds corrector. This is for the Reynolds corrector, or this one is for the current corrector. So in the case of the Reynolds corrector, this one is like RQ, and we are taking 3/2 norm, because I'm using holder. So L3 norm, L3/2 norm. Right. And then from here, we have, again, L1 norm of this. And then you also have something for the phi q. So, but since this will be same size, I will just leave this part as an exercise. Sorry. Then let me just continue. Then what you have is the following: lambda q, delta q 1/2, RQ 1/3. Just use inductive bound. And then from here, you get delta q plus 1. And yeah, L2 norm is 1, so this is unisize. And we want to say this one is bounded by 1/10 delta q plus 2, 3/2 RQ plus 1. If you remember the computation for in the previous case, so previously this one was the size of transport error, size of the, Nash error, they're same. So Nash stress error in the C0 scheme, and this one was bounded by delta Q plus 1. I want to also include, let me first rearrange this. So here, I want to write this one in this way, like lambda Q plus 1, delta Q 1/2, and delta Q plus 1, 1/2. So this one was previously the size of Nash error. And then the remaining one is delta Q plus 1, 1/2, and there's RQ minus 1. And this quantity was bounded by delta Q plus 2 if beta is less than 1. Okay. Okay. I was a bit lazy. So you also need to do it. Yes. I will leave it as an exercise. Okay. So this has size of delta Q plus 2. And then what's remaining here is, okay, delta Q plus 2 times delta Q plus 2 1/3 and RQ plus 1 minus 1. So you need to compare this with this. And the good news is that here the power for this power above this intermittency parameter is -1, and this is -1/3. So when you invert this, so when you multiply by RQ plus 1 on both sides, you actually have a gain from intermittency. Remember that this is a small parameter. And this is enough to upgrade from delta Q plus 1 to delta Q plus 2. So this will also close as long as beta is less. So this is how you get 1/3 by using the gain from the intermittency.
It's not sharp, you can improve. This is very good process. You can improve here.
No, I can't go further than this, no?
But you are already assuming that the Nash error is less than delta.
No, so I just to make the computation easier. But if you, okay, another way to do it is you really do computation for all this.
There is still a room because that is less than delta Q plus, not exactly equal.
Sure, sure. But the rule, okay, yeah. If you use that rule, maybe very carefully, maybe you are able to achieve 1/3, but yeah, you can go. Okay, so then now let's talk about the difficulties. Yes. Right. When you take summation, or when you send Q to infinity, yeah, it will get larger. So that's why you couldn't have your eventual solution to be in L infinity. It's L infinity minus. But if you use interpolation, so any fixed p be less than 1, less than infinity, and if you interpolate between L1 and L infinity, you can always make the convergence. So that's how, yeah. Any other questions? Yeah. So of course, I didn't treat many other terms, but if you believe me, at least at the heuristic level, we under this beta is less than 1/3 condition, you can close all the errors. And now, so this is only at the heuristic level. As Ujjwal asked me earlier, making this work is a different story. It requires a lot of work. So let me now talk about what are the difficulties in proceeding this heuristic. Five. So one thing that we ignore so far is, yeah, what happened in the intermediate frequency, the frequency less than lambda Q plus 1. Okay. So let me just describe a bit more of how can it go wrong. So just to consider simple case, let's just start like this. We start from the initial approximate solution, and let's say the frequency of R0, you can also consider phi 0, but at this moment, let's just think about the stress error. And then let's say it has a frequency localized at lambda q. And then to correct this, you use this intermittent perturbation, and whose maximum frequency will be lambda 1. And then if you use this intermittency parameter, the minimum frequency will be lambda 1 times R0, which is actually lambda 0 times lambda 1 raised to the power 1/2, which is actually almost like lambda 1. So you will have error in this range of frequency. So let's consider one error. So again, let's just think about the oscillation error, which is given as follows. R Q plus 1, and then which one was defined as inverse divergence of essentially A square, and then the not equal. And if the projection operator is at the frequency, the worst case, lambda 0, lambda 1 raised to the power 1/2. The gain from inverse divergence is only the inverse of this number. It's much worse than before because previously we gained 1 over lambda 1, but now we have much large factor. So this actually, if you do the computation, R3 over 2, you can't really get delta, here the delta 2. You can't get. But the observation is following. So what's the size of error here? We want the size of error to be delta 1. And here we want the size of error to be delta 2. And we are considering error at the frequency in between. Perhaps if we can get the size of delta 3 over 2, this looks okay. So my claim now is that actually this error, okay, since we only consider this one, let me just put it the last and then first. Okay, let me just write it this way, it's a bit ugly notation. But the size of this oscillation error with the lowest frequency can be bounded by delta Q plus, sorry, not 1, 3 over 2, right? So this is what I want to show. Okay, but for this computation, we need the following lemma. What I promised to Ujjwal. Okay. The lemma is the following. Let's say rho is a periodic function with period lambda times r in the 2 dimension. Okay. And then when you take the derivatives, actually the cost is lambda. And so this one is bounded by some constant, which is almost like L1 norm size and lambda n. And now what I want to say is that if you consider the frequency, so this will be the minimum frequency and this will be the largest frequency in effective sense. And if you choose some lambda 0 in between, you actually have the following bound. When you take a projection operator at this lambda 0 to low and compute this LP norm, then its size is C1 times lambda 0 over lambda r 2 minus 2p. Okay. So, okay, this one you can just consider it as a phi r square as a law. Then whose L1 norm was, because it's normalized in L1 norm, actually the C1 is 1, and which has the derivative cost was the lambda q plus 1, and then lambda r was the, if you consider r as an intermittency, that was the periodicity. So that's how I'm gonna apply. And then what I want to tell is that if you take the projection operator somewhere between the minimum frequency and maximum frequency, in terms of LP norm size, you actually have gain. So if you just use the this estimate, you can only get, so our RQ, so here RQ is the same with RQ, and we only get number is correct. Okay, RQ. Okay, 2 over 2. Wait, number doesn't match. I think I did something. I think this should be correct. And then okay, so I'm applying for the squared one. So it's actually 2p and squared. And then the size will match. Okay, that's right. So if you just use, okay, maybe let's do the computation just to make sure. Square, and then I want to know LP norm. This is the W2p square. So now if you plug 2p into here, over 2 minus 1 and times 2, then you will get 2 over p and 2. So it's matched. So if without this projection operator, the original size that we have was this R2p minus 2. But here there's extra gain, lambda 0 over lambda 2 minus 2p. So there's extra gain in terms of size. And you have more gain if this lambda 0 get close to the minimum. And this was actually why when you apply L infinity norm, when this lambda 0 is the largest frequency, it was the worst case. Okay. So now, by using this, I want to prove the claim. Okay. So I want to consider this error. Over 2, no? Let's consider only when it's R. You can do the same way for the current corrector. And then from inverse divergence, you have this lambda 0, lambda 1 raised to the power 1/2. From here, okay, you apply by using the coupling lemma. So this one is almost like R cubed. Let me just like, R0. And then 3/2. And then here you have the projection operator. So here, having this projection operator is important. Okay, in this case, it's actually not that important. Well, okay. No, it is important, sorry. And then this one is lambda 0, lambda 1, 1/2. And then the size was lambda 0, and then delta 1. And then here, okay, if you apply that lemma, this 1. So this is at the minimum frequency. So, and here, if you look at this quantity, the minimum frequency is lambda times R. So this will be just 1. So the frequency at the right-hand side will be just bounded by L1 norm of the law. In our case, law is this WR and W1, and whose L1 norm is 1 because it's L2 normalized. So this is it. So this is all. And then we want to show this is less than delta 3/2. How much time do we have? Okay, I will skip the computation. If you do, you can see why this is. So what does it mean? So what it means is the following. So if you consider the error at the low frequency and error at the largest frequency, this will be actually a bad idea because the size at the low frequency is much larger than the size at the high frequency. So you should treat this error at different iterations. You should correct separately. So what we actually gonna do is you actually decompose this error into the small pieces based on the frequencies. And then at the first step, you actually correct the minimal, the error at the minimal frequency. And then you correct again the perturbation. I will explain why this is a perturbation, why the perturbation occupied this much, but in a minute. But let me just first. So it will occupy. You will add a perturbation whose frequency range goes up to lambda 3/2. So this is a new perturbation. So it will generate a new error. Then combining this remaining error and the new error. So this will be, so this one was R1, also R1, and this will be R2. So this will form our next step error. And then you just continue. Again, you correct the next smallest error, and then add the perturbation, and then just combine the remaining one with the newly generated, and continue. Okay. Yes, so I correct this little bit, and then it actually generates this little bit eventually. So maybe, and maybe for the reason why I add the perturbation at this amount of frequency, at this amount of intermittency is the following. So to make this heuristic computation works, what you need to do is when you write this RQ, where is RQ? So, okay, maybe first let me explain this in a general context. So RQ here, I mean, here lambda Q comes from the derivative cost of RQ. So this one is the derivative cost. The error that we correct, it can be also current error, divided by the maximum frequency of our solution. So let's say again, the derivative cost of our correction, so perturbation. and raised to the power 1/2. And if you write this RQ in terms of the derivative cost of error, then the exponent should remain the same. And okay, and then you can just make this heuristic computation keep working, even though you make all this division. And that means that, so at each step, the derivative cost of error is fixed. And then now the intermittency parameter is also fixed. So it determines the maximum frequency of the perturbation. So that's how I get this lambda 3/2 as the maximum frequency. And then if you use intermittency, this is the range of the frequency that it will occupy. Okay, so let me just summarize what I explained. So if you keep iterate, what you will see is the following. At Q step, you will have error which occupies wide range of frequency, because even though you start from the initial error, which has a frequency concentrated one, but after a few steps, you can see that the error occupied wide range of frequency. So it will do. And the second thing is, if you do this way, you also need it's a more practical issue. You need a labeling for all these intermittent frequencies, which is a bit inconvenient. So we just introduce the parameter n bar. You can just treat this as a 1 there, but we just want to put the, some labeling for the intermediate frequency. So at Q step, the RQ, or actually even phi Q, will occupy this range of frequency. So this is, let me just talk at the level of RQ. And then we'll just divide this error into as follows, like from lambda Q plus 1 to lambda Q, the frequency, and then lambda Q to lambda Q plus 1, and so on. And we denote each of them by lambda Q, Q, lambda Q plus 1, Q, and so on. So the superscript corresponds to the maximum frequency index. And then, as I described, what's happening at Q plus 1 step is the following. You correct the error, which has the minimum frequency, so this one, by adding perturbation. So let me correct error. So this error was RQQ by the perturbation whose maximum frequency is lambda Q plus n bar, and the minimum frequency is lambda Q plus n bar over 2. So somewhere. So this will generate again error in this range. So, and then combining the remaining error with the newly generated error, you have RQ plus 1. So if I draw RQ plus 1, it looks like this, lambda Q plus 1, lambda Q. So this error was removed by using this correction. And then the new error will have the following range of frequency. So this is RQ plus 1. And then you continue. So you correct this bit, and then you have another wider range of error, and there's especially you also have a creation of some error at this frequency. Then you are just moving, like you're just keep moving. n bar is something related to the number of partition that we're gonna take. So here the problem is if you just want to keep this parameter, the way this notation, then this one it will be almost like a lambda 1/2, and I'm gonna divide this into the bunch of small pieces. Then you need labeling just for all this small one, which is very inconvenient to use fraction. So yeah, here, from here to there, you need to use a bit of analogy, but that's a much cleaner, that gives a much cleaner way of writing. Do you have any other question? If not, let me stop here. So Vikram will continue, I guess, from here. And even after this, there are some difficulties, but Vikram will show you how to handle.
Thank you for this beautiful lecture.
Thank you.